stereochemistry of the E2 reaction is very important. So it turns out that we have to have this special arrangement between the H that's being lost and the leaving group that's leaving. So if we look a little bit closer at this little diagram that I put together, what we have here is a Newman projection. Right now, in this Newman projection, we can see that we have an H atom here, and then our leaving group is back here. So this is a Newman projection of this molecule here, looking down that bond, if we were to look down that bond, right? So here we have a dihedral angle equal to 180 degrees. And when we have this arrangement, we have something called anti-coplanar, also sometimes referred to as anti-periplanar. So we're not going to get into much about the orbitals and how they overlap with each other and stuff when we look at the coloring of the lobes here. But this requirement is necessary for this reaction to proceed. So one of the outcomes that we have here that may not be totally obvious is this, is that we often, when we draw out our reactions, we often keep carbons in the plane, and then we put halogens or whatever else the leaving group is pointing out on a wedge or a dash. So we don't usually keep those in plane and draw the carbons out of plane. But let's see, in this Newman projection here, let's see what else is 180 degrees from each other. So if we look at this carbon that's in the front right here, this carbon right here, remember that that carbon is this. It's this bulleted carbon, right? And then we have these R groups. And I want to label these things. I'm going to circle one of them. Let's choose like black. So one will choose black, and the other one, why don't we just circle it in red. So when we look at the structure over on our left and turn it around, right, the red atom here is on this side, right, and then our black carbon is over on that side. So let's do the same thing over on this carbon. Let's identify where those are in the Newman projection, okay? So as we look at those, what I want to do right now is I want to put in, I want to circle one as being red and one as being black here. So in this case, what I want to do is circle this dash guy as being black, and then this wedge as being red. So now when we take this thing around, we would have this group here being the red, and then that group would be the black. So notice that we have here these black circled carbons. They have dihedral angles of 180 degrees also. They're anti-coplanar to each other. So these black atoms here, so these groups here, those two groups, these things have a wedge dash relationship, right? You could say in some ways that they're trans to each other, right? In a ring, we would say that they're trans. So they're a wedge dash relationship. So in order to get elimination to occur, we have to have a wedge dash relationship, or in plane, we would see them as being just anti to each other, right? It's easier to see that way. But we're not going to waste our time redrawing every structure so that our leaving group and H are in the same plane. So when we look up at this, for example, right, that iodide is on a wedge. So at this carbon, right, if we're looking at that one, we have an H that's pointing out and an H that's going back. So which one is anti to this? Well, that H right here is anti to this. So it would specifically be that H that's lost. You may think, why does it matter? We're going to see why it matters. It does matter. All right, so we have to have this anti-coplanar arrangement. And then, of course, that leads us to our alkene right here, right? So there's your alkene. So if we don't have that anti-coplanar arrangement, then the easiest way to kind of explain this is that you have this repulsion between the base that's coming in here and the leaving group that's leaving. right? So it's an unfavorable interaction. That gives us a dihedral angle of 0 degrees in the eclipsed conformation there. Now what this leads to is something called Zaitsev's rule. And I know in our last little lecture segment we mentioned what the Zaitsev's product was. So what this says simply is this. In elimination reactions, this is E2, and by the way, we haven't seen E1 yet, but it pertains to E1 too. The product with the most substituted double bond is preferred. It's the most stable. Now we already intuitively know this because we talked about the heats of hydrogenation in our last lecture and saw, for example, that a tetrasubstituted alkene was more stable than a monosubstituted alkene, right? Remember this little table that we looked at. So that this table confirms Zaitsev's observation that the most substituted alkene is going to be the most stable and typically the most preferred. Now there are going to be some cases where we get something called the anti-Zaitsev's product.